Okay, let's take a look at today's lesson. Today's lesson is our first day on vectors. The vector lesson on Monday is mostly calculators, so if you don't normally bring your calculator with you, then please be sure to make yourself a note and bring it with you on Monday, because you will need a calculator for Monday's lesson. All right, let's talk about vectors. Vectors in relation to parametrics. They are so closely related. It's quite easy to jump from one form to the other. So let's talk about that, because that's pretty important as we go through our vector lesson, because there'll be a lot of references to parametrics. So if you'll notice, the way that these equations are written, they're written in parametric form, but they are talking to us about finding the velocity vector. So just changing the way that it's written changes the form that we're looking at. So let's talk about what these look like graphed, the difference between parametrics being graphed and vectors being graphed. If we graph these two equations in parametric mode, which you probably have done on your calculator before, you go into the mode and change it to PAR for parametric, you'll have the x equation and the y equation. And what the calculator, or to graph, what you would do is you would substitute your t value in. Remember, we've done that before. Get a coordinate point, and it creates a curve. So the x and the y at a particular time create a point, and it creates a curve. A curve, something like that. We would create a curve. A vector, the same set of equations could create a vector equation as well. All I would do is put my, vector comma like that, and that wouldn't be there. The x one goes in the first slot and the y one goes in the second slot. So that's a vector equation. The way those graph, that type of problem graphs, is it basically maps the vector to each point on the graph. So instead of mapping the x and the y together like the parametrics and creating a curve, what a vector equation does is each of these points is measured by a vector. That's really gives you the exact same graph, but it's created a completely different way. Completely different. So I just need you to understand they are very closely related, and problems like this one go in and out of parametric and vector form just fluidly. They just move in and out, and that's okay. That's not a problem. All right, so it's written in parametric form, but they're asking us for the velocity vector at a particular time. So what I would do is I would go ahead and find the velocity vector. And we just take the derivative of the x and put it in the first spot, and the derivative of the y and put it in the second. Our vector is in horizontal and vertical components, x, y. So we take the derivative of the first one, and we get 6t squared minus 10t. And then the derivative of the y of t would be 8t cubed plus 3t squared. And that's our velocity vector. Okay? So we then would substitute a 1 in there to get the velocity at 1. And so that's just some arithmetic. Just put your 1 in there, and you get a negative 4, 11. And so that is the value of our velocity vector when t is 1. Okay? Pretty straightforward. The concepts that we're working with are old concepts that we've been working with for a long time. We are just applying them to different types of equations. We're looking at velocity or vector equations now. So acceleration vector, I would just find it first so that I can use it. So we would get 12t minus 10 and 24t squared plus 6t. That would be my acceleration vector. And so they want us to evaluate it when t is 1. So we do the same thing. We plug a 1 in there, and we get 230. Okay, is everybody okay so far? Okay. So We've talked about magnitude. You have, I'm sure, in pre-cal we talked about vectors and magnitude. If you've taken physics, you've probably talked about magnitude and vectors. If we want to find the magnitude or length of a vector, it's a formula, right? I mean, it's a square root. It's like Pythag. If we want to find the magnitude of the position vector, we would do our x of t squared plus y of t squared and take the square root of that. So let's talk about what that means. What would it mean if I were to find the magnitude of the position vector? Let's look at this particular situation up here. If I were to find the magnitude of a position vector, what would that give me? It would give me this distance, right? The distance of the vector, that's what it would give me. If I found the magnitude of this particular vector, it would give me that distance, the position distance, just that one vector. It's not going to give me, like some students were a little confused earlier, it doesn't give me the arc length of my graph. It just gives me the magnitude of the position vector, just gives me the length of one of the position vectors. Okay? All right. So if we want to do the magnitude of the velocity vector, same formula, but we would use the velocity vector instead. So we do x prime of t squared plus y prime of t squared. And this one's meaning, what we would use this for, is one use is speed. So the magnitude of the velocity vector is also called the speed of the object moving along the curve. Okay, so that would be magnitude of velocity. Okay, let's look at magnitude of acceleration. So that would be basically x double prime of t squared plus y double prime of t squared. Now the use of this, I've used it before in calculations. I haven't really used it in a context like these two, like finding one of the unit tangent vector or something like that. But I haven't used acceleration. I mean, I'm sure there are uses for it as well in applications. I just have not done that. And you won't do that in BC. Okay, so let's take a look at number 2. It tells us that a particle moves in an xy plane so that any time t, where t is larger than or equal to 0, the position is given by this, this set of equations. Find the magnitude of the velocity vector when t is 3. Okay, well let's find the velocity vector first. So 2t plus 5, and then we have natural log, so that's going to be, we have to chain that. So 2t over t squared plus 4. That would be my velocity vector. And we could label it if we want. And so now we would substitute a 3. Well, we need the formula for magnitude. So we would just use our magnitude formula and substitute a 3 in there. Alright, so let's see, if we put a 3 here, we would get, 11 squared plus, and we put a 3 in here, 6 over 13 squared. That's kind of messy. We would have probably a calculator for that one, or they would just have us leave it like that. So if I put that in the calculator, I would get approximately 11.0096. And we could certainly round to the thousandths or just truncate at the thousandths. Okay, how are we? We good? Okay, let's go to the next page. All right. Oops. Okay. Ready? Let's take a look at number 3. What that does, we have a particle moving in the xy plane so that, and again we're given the positions, We're also giving a restriction on the t-values. The t-values go from 0 to 2 pi. And the path of the particle intersects the x-axis twice. Write an expression that represents the distance traveled by the particle between the two x-intercepts. Okay, there's a lot of stuff in there. Let's kind of pull that apart. The first thing we need to look at, or just notice, we have some positions and we have a restriction. So we need to take that into account. It tells us the path intersects the x-axis twice. Okay, we're going to have to do something with that. Let's think about that for a moment. Intersecting the x-axis. What do we know? Let's just think about the x-axis here. What do we know that all points on the x-axis have in common? The y value is 0, right? Not the x value. The y value is 0. So if we take our vertical representation, our y, and set it equal to 0, we should get where it crosses the x-axis. Right? Okay, so that's what we're going to do. So 0 equals 1 minus 2 sine t. So we solve that. We remember our fantastic trig formulas and such, how to solve trig equations and unit circle values, all that awesome stuff. Now we are limited between 0 and 2 pi. Okay, so that's all we need to worry about. So let's think about this. Okay, unit circle. Sine is 1/2 at pi over 6 and 5 pi over 6. Okay, good. Now we want distance traveled. Let's think about that. So the distance on the arc. What would represent distance on the arc? Well, magnitude would give us our vector lengths, but what's going to give us that distance along the curve? Our arc length formula. Right? Our arc length formula is going to give us the distance along the curve, not individual distances of vector distances, but the entire distance on the curve. And that is that big square root formula that we looked at, I think, yesterday with the integral. Do we remember what the formula was? What did we put in there? Yes, we squared. Remember we did the derivatives and then squared them. Remember that? The derivative of each one and then squared it, and we added them together under the radical. Remember that? That's the formula that we're looking for here. So we would do the derivative of x, and you don't have to write them separately. You can stick them right in this formula, but I'll go ahead and calculate them separately. The derivative of x, the derivative of root 3 is nothing. The derivative of negative 4 cosine, remember the derivative of cosine is negative sine, so the negative crosses out, and I'm left with 4 sine t. And then the derivative of our y component, let's see, is that 0. Derivative of sine is cosine, so what? Negative 2 cosine t. All right, let's fill that into our formula. And they tell us not to evaluate, which means probably we would have had a calculator for this. You know, so don't evaluate, just set up. All right, so we have 4 sine t quantity squared plus negative 2 cosine t quantity squared. Now, our equation is in t's, so our bounds also need to be t bounds, right? Which we actually found over here from pi over 6 to 5 pi over 6. And this would be our, dt. This would be our representation of the distance between the x-intercepts. So it was a fairly complicated sounding question, but if you pull it apart into different pieces, hopefully that will just flow and you will be able to discover what it is you're supposed to do. Okay, let's take a look. Before we do number 4, I just want to call attention to this part here in the middle that I put. Most of us probably already have this implication, but I'm just going to write it out. So go back to the formula. It's dx dt and dy dt, right? Yeah, so we do have to, and this is just the position, so we do have to do the dx dt and the dy dt to put in the formula. Okay. All right, so this part that I have here in the middle, this box, probably you would have caught in the implication already, but I'm just writing it out. So when the particle is at rest, we already know when dealing with functions, that's when the derivative is 0, right? The velocity is 0. And for the velocity vector, for a particle that's written in a velocity form, the vector form, to be 0, both components have to be 0. The horizontal and vertical component of the velocity has to be 0, not just one or the other. So keep that in mind. It's both of them that have to be 0. So that takes us to number 4. If we have a particle moving on the xy plane and we have a position, what values of t is the particle at rest? Okay, so let's do that. Kevin, you're going to need to put your phone up. You don't want me to. Okay. So let's do our, we need a vector, our velocity vector equation for this. So let's do that. So we have 6t squared minus 30t plus 36. That would be our x component. Our y component would be 3t squared minus 6t. And we want to know for what values is it at rest. Okay, so what we're going to have to do is set each of those components equal to 0 and see what the t values are there. So on this first component, it has a common factor of 6, so I'm going to pull that 6 out. And so let's factor that. So t minus 3. So we have 2 times when the horizontal component is at rest. So in other words, it's not moving horizontally when t is 3 or t is 2. So let's find out about our vertical component. And let's set it equal to 0. We'll factor that. So we have t is 0 or 2. Okay. So at what time is the particle completely at rest? 2. It has to be at rest on both the horizontal and vertical component. It can't be at rest at just one. What do you think that means, though? At time equals 3, when my horizontal component is at rest, what does that mean in relation to all the rest of the, the other parts of the vector that are going on? Yeah, it's only moving vertically at that time. That's what that means, because there's no horizontal movement at 3. So what we're looking for is where they are the same. So it would be at t equals 2 because my velocity vector is 0, 0. That's what my requirements are, is that both components be 0. Okay? All right. Let's take a look at our last one. Here we have a particle moving. Okay, we have a position. Oh no, we have a velocity vector this time. Oh good, something different. We have a velocity vector, and we are told that at time equals 0, the position of the particle is at 7, negative 4. Find the position at t equals 1. Okay, a couple different ways to do that. I'm just going to work us through just doing an antiderivative. Let's just do it that way. That's one way to do it. So we'll do an antiderivative of each one of these to go backwards to the position, and then we'll find our c with this information right here. So that's one way to do it. So our x of t is going to equal the integral of 3t squared minus 4t. That's what's going to give us our x of t, right? So let's find that. We do the antiderivative. So what does that give us? Okay. And we find C. It tells us when t equals 0, our x-coordinate is 7. So it's 7 when t equals 0. So our C value is 7. So our x of t is going to be t cubed minus 2t squared plus 7. Okay, we would do the same type of procedure to find y of t. So we would do the integral of 8t cubed plus 5. Then we do our antiderivative. So let's see, add 1, get 4. So that'd be 2t to the 4th plus 5t plus c. Then I know that at t equals 0, my y coordinate is, or component is negative 4. So substituting that in, we get c equals negative 4. And we have our y of t. Y of t will be 2t to the 4th plus 5t minus 4. Okay, so doing it this way, you do have the positions and you can use them for various things. A lot of the problems are going to have parts A, B, and C where you probably will have to use them for various things, so I wanted to work it out that way. Now we would substitute a 1 in to each of these to get our location or position. So we put a 1 there, and we get 6. And we put a 1 here, and we get 3. So that's our position at 1. Okay.